Get ready for another massive module, this time the Random Access Memory, or in short, RAM. RAM is one of the most important computer components when it comes to the live performance of your machine. After this module, you will understand the different types of system memory and the way they're being used in computers. Now, this is your chance to dive in a little deeper and understand what purposes the RAM actually serves in computers. Although the RAM topic has already been mentioned and discussed in previous modules, sometimes as system, primary, volatile, or internal memory, you might still be asking yourselves, for crying out loud, what is RAM? As you might have noticed, the memory module is the longest in this chapter, and there is a good reason for that, as memory is the essence and the cornerstone of nearly everything in computing, be it for long-term storage, running processes and applications, executing commands, and the operating system itself. It's all about memory allocation, and most of these tasks highly depend on the RAM. So what is RAM? RAM stands for Random Access Memory, and as stated previously in the chipset module, RAM interacts directly with the CPU through the NOT bridge, which indicates it is a high priority and high performance component. Therefore, it requires special attention from the entire system. As mentioned before, the RAM is a volatile type of memory, which means that unlike hard drives and ROM, when it loses power, its content is completely flushed. However, compared to ROM, and other storage technologies, RAM is significantly faster, which is why it is used for real-time tasks. When we launch a program, the hard drive sends the relative data for that program to be loaded into the RAM, where the processor can access it much faster than going directly to the hard drive. If ROM or storage devices can be considered as dormant memory, used for the long-term storing and archiving, and independent of power, the RAM allows us to perform live operations and interact with the machine using direct input and output operations, but requires power to keep the data intact. Let's make a quick comparison between ROM and RAM. This will shed some light if you're still not there. The main differences between RAM and ROM. Speed. RAM is way faster than ROM, which is why real-time read and write operations are performed on the RAM and not on the ROM. Data retention. As ROM is non-volatile, it can retain data perpetually. RAM, being a volatile type of memory, can retain data as long as power is directly provided. Usage. Due to its non-volatile nature, ROM can be used for long-term storage needs, such as firmware or BIOS, while RAM is used for the short term, in real-time tasks only. Operation. ROM is usually operational before the operating system has booted, but once the data is loaded into the RAM, it remains there also after the boot process completes. Storage capacity. Lastly, RAM has a higher storage capacity than ROM. For instance, I have 16 gigabytes of RAM installed on this machine, but the ROM, which serves to store the firmware, stores only a few megabytes of data, not to confuse with hard drives or flash storage devices which store up to terabytes of data. ROM is not designed to store large amounts of data. Scenarios. In this section, we'll go through different real-life scenarios that will help you understand some major differences between resources that have already been discussed earlier. If computer performance is still unclear to you, this section was created to help you see the different functionalities of each component. System performance is generally measured by three components: the CPU, the storage, and the RAM. Trying to understand the interaction between these three components and the direct effect each one of them has on the machine's performance might be a little frustrating and confusing at first. To simplify everything, I came up with a friendly analogy to elaborate the purpose and importance of each component. But first, let's briefly recall their roles so we can better understand the functionality of RAM. First, the CPU is the brain and the main processing mechanism of a computer. It determines how many operations can be completed per second. The number of operations per second is measured by gigahertz. For example, 3.6 gigahertz equals 3.6 billions of cycles per second. This can be compared to the writing speed of an individual. Some people write faster and others write slower. Core. Core is a partitioning of the CPU's processing capabilities. It is responsible for the distribution of processing workloads among different tasks. Now, the idea of cores can be compared to multiple people writing at the same time, so the writing speed isn't affected, but each person can be working on a different document or task, let's say, separately. Multiple cores can be very useful when running multiple applications where read and writes need to be performed simultaneously on separate tasks. Storage. Storage is a space for storing large amounts of data, which can be read, written, or modified once loaded into the RAM, or remain dormant after a shutdown. The storage component can be compared to the amount of paper those people have for writing their projects. The more paper, the more space is available to insert data and store it. And just like paper, hard drives can retain data for quite a while. RAM. RAM is the workspace to which the static data is loaded in order to be dynamically modified. So RAM in this case is our actual workspace. We can compare it to a desk. The more RAM we have, the larger the desk is, meaning that more people can actually sit down and write their tasks. The RAM or the desk has to interact both with the storage and the CPU cores, or metaphorically speaking, the larger our desk is, the more people can engage and the more paper we can write on. Let's try to use the following scenario to better understand the idea of system performance and the role of RAM. So we have one i7 quad-core CPU, 5 GB of HDD storage, and 2 GB of RAM. In this scenario, let's imagine one team of 4 employees all working on the production of a book. Each employee is assigned a specific task. We have an author, an illustrator, a proofreader, and a publisher. There is only enough room for 2 employees to work on the desk, which means that the 2 remaining employees will either have to switch with their colleagues constantly or remain on standby for a while. Lastly, the team budget can afford only 200 A4 pages for their whole project. Each person can work on a single page at a time. Now you start realizing where the main problems lie. Some compromises need to be made. The paper quantity might not be sufficient for the entire project, and the desk is not large enough for 4 people. This would require new adjustments in their rotation. We have a decent amount of processing power, a limited workspace, and low storage capacity to store the content. Therefore, there is also a decrease in the processing efficiency. While 4 people are engaged for the same project, but only 2 of them can work at the same time, and nevertheless, there is not enough paper for them to write the entire book. The bottlenecks in this case would occur at the low capacity storage level and the limited workspace. To correct this, more paper and a larger desk need to be supplied. We can easily compare this scenario to what happens when we work with a computer. We can say, for instance, that our project is creating an online tutorial for YouTube, just like this one. For this purpose, we might need 4 applications running at the same time: Microsoft PowerPoint, Google Chrome, Adobe Photoshop, and a screen recorder, which consume a certain amount of memory and CPU resources. We'll also need a decent amount of space where we can actually store the media files such as slides, photos, videos, and of course sufficient processing power and a workspace large enough to run those 4 applications at the same time. Opening the Task Manager or the Resource Monitor is a quick way to check how many resources are consumed by each application. Once open, it would show us the following. Adobe Photoshop occupies 650 megabytes of RAM and 0.1% of the CPU before processing. Ice Cream Screen Recorder occupies 250 megabytes of RAM and 14.2% of the CPU before starting to record. Microsoft PowerPoint occupies 162 megabytes of RAM and almost no CPU. And Google Chrome occupies a total amount of 581 megabytes of RAM and 0.3 of CPU, but it can go higher, up to 3 gigabytes of memory depending on the number of processes. Those applications alone occupied 1,643 megabytes or 1.6 gigabytes of RAM and 14.6% of the CPU. Here are a few notes. 1. Those programs are running in the background when untouched. The moment we start adding tabs to Google Chrome, loading projects in Photoshop, or recording video or working with large presentations on PowerPoint, much more resources will be consumed. In fact, Chrome alone can eat gigabytes of RAM. 2. There are hundreds of other services, processes, and tasks working in the background as part of the operating system. Windows alone in a 64-bit architecture consumes at least 2 gigabytes of RAM. So how well do we do to accomplish these tasks and complete the project? Let's check each resource. We have more than enough CPU to run all applications at once, even during the data processing. 5 gigabytes of external storage might be very limiting, and there is almost no chance that they would be sufficient for high-quality raw video materials, slides, documents, and labs. Even low to medium quality tutorials of 6 to 8 hours would still require at least 10 gigabytes of storage, just to be on the safe side. Lastly, we have enough RAM to run the operating system alone. Anything else would create a memory bottleneck, so although the CPU is powerful, the computer will be struggling to load all the applications and services at once, and would desperately try to use virtual memory to overcome this problem. However, it will eventually crash at some point. Let's try another scenario. Our new task is editing and exporting a video clip using Adobe Premiere Pro. The video quality must be high definition of 1080p and at least 5 minutes long. Let's check the Adobe Premiere system requirements first. We need a 6th generation Intel CPU, a minimum of 8 gigabytes of storage, and 8 gigabytes of RAM. So to summarize, we need at least 8 gigabytes of RAM, a 6th generation CPU, a powerful GPU, and about 8 gigabytes of storage for the software installation. These are only the basic requirements. In reality, always consider having more than the minimum requirements. And there are additional resources to consider. We will need more RAM for the default operating system services and processes, as well as for additional applications we might run in the background. Our current OS occupies 40 gigabytes of RAM already. We need more space for the raw video materials and for the final output. On the table on the right, you can see a matrix showing different resolutions, bit rates, and size per minute. The lowest 1080p resolution uses a bitrate of 30 megabit per second. We will use a bitrate of 30 megabit per second, which is 3.75 megabytes per second, 225 megabytes per minute, and 1125 megabytes per 5 minutes video. So we need to consider an additional 1.2 gigabytes of storage space. Scenario number 2. We have a Pentium 3 processor, 120 gigabytes of internal high-speed SSD storage, and 16 gigabytes of RAM. Our new task is editing and exporting a video clip using Adobe Premiere Pro. The video quality must be again high definition and at least 5 minutes long. Overall, we require an Intel Core 6th generation. Our Pentium 3 processor is an old model and will not be supported on the newest versions of Adobe Premiere, not to mention any modern computer nowadays. We'll need 54 gigabytes of storage. While the OS occupies 40 gigabytes, Adobe Premiere occupies 8, and additional video materials, including the final output, would consume just a few additional gigabytes. Our operating system, Adobe Premiere, and the additional programs and services in the background can easily be supported on our 120 gigabytes SSD. And finally, we have more than enough system memory to run both the basic operating system services and Adobe Premiere itself. The RAM requirements are 10 gigabytes for the OS and Adobe Premiere alone, leaving us 6 gigabytes of spare memory to play around with. For a comprehensive list of Intel Core generations, please visit the link on the right.